Okay, so for cross product, I am expecting that most of you are going to set this up in the 3x3 determinant way, like what we were talking about yesterday. Is that right? Is this what most of you guys are going to do for this? Okay. And remember, cross product's not commutative, so A cross B and B cross A are not the same, although the only difference is you're going to get the negative if you do it the wrong way, right? But if it's A cross B, the A components go in the middle row, so 2, 3, 1 goes here, and the B components go at the bottom. So 5, 1, negative 2 goes this way, right? And when you do cross product, you get a vector. So I'm just going to write this as a vector answer in the same format I used here. So the top part will be the I component. The I component, when you're finding the determinant of this, the I part is the determinant of I's minor, which is the 3, 1, 1, negative 2. So what is the determinant of 3, 1, 1, negative 2? Negative 7. Okay. All right. And then J, remember from what we did in matrices, J's in a negative spot. So the answer for the J part here is going to be the negative of J's determinant. The minor for J is 2, 1, 5, negative 2. So if you do the determinant, it's negative 4 minus 5. That would be negative 9. But since J's in a negative spot, we use positive 9. Is that fine? And then K is back to straightforward. The minor for K is this, 2, 3, 5, 1. What is that determinant? 2, 3, 5, 1? Nope. Oh, I know what you're doing. You added.
Negative 13.
Yeah, it's 2 minus 15, right? Not 2 minus 8. So, yeah, negative 13. Okay? All right, are we good? So that's the answer. That's the cross product, right? And if you want to check your answers, the cross product is supposed to give you a vector that is what in relation to these two? Perpendicular. So if you dot this with either of these, you should be getting what? 0. You actually should be getting 0 for both cases, right? Otherwise you messed up the cross product. Okay, now, number 2 uses a bunch of terms we talked about yesterday. So U and V represent two vectors that are parallel to N. Okay, yesterday we used the term parallel for vectors. I said it's not quite the same as parallel for lines. If two vectors are parallel, what do we know about them? They're scalar multiples of each other. So U and V are both going to be scalar multiples of N, okay? But they're described differently. U is a unit vector. That term came up yesterday. What does that mean? Magnitude is 1. And pointing in the same direction as N. What information does that give you?
It's not negative.
What about the scalar?
It's not negative.
Right, it has to be a positive scalar, okay? So, and then it says V points in the opposite direction, so that's going to have a negative scalar, and the magnitude of V is 5. And the question is find the components of both U and V. Okay, let's deal with U first. What am I going to need? U is a scalar multiple. We know it's a positive scalar multiple of N. How do I figure out what's the appropriate scalar to multiply N by to end up with U? What do I need that I don't have yet? Magnitude of N. Yep. Okay, magnitude is square root, right, of, we have to square all these. So we're going to get 49, 81, and 169, right? That is 130 plus another 169 would give you 299, right? Okay, all right, so now I have the magnitude of N. What do I do with that to get U? How do I use that magnitude value? 1 over that, right, is my scalar. So I know root 299 is not a nice number, right? It's not, 299 is not a perfect square. But 289 is, right? 289 is 17 squared. So if this had come out to 289, root 289 is 17, that would mean this vector is exactly 17 units long. So if you want a vector that's 1 unit long, you would take 1/17 of that, right? So here, this is the exact length of it. So 1 over root 299 times the original vector, negative 7, 9, negative 13. This would give you a vector whose length is exactly 1, right? Now, you can write a vector like that with a scalar in front, but in this question, since it says find the components of both U and V, if I asked you what's the x component of U, what would you tell me? -7 over root 299. You have to incorporate the scalar in there, right? So this doesn't actually clearly communicate what the components are because it's not obvious that you know to include the scalar in there. So if I was writing down what the actual components are, I would just put the scalar inside here like this. Okay, these are equivalent, but this more clearly says what the what the components are. Does that make sense? Okay, now what about for V? It says V goes in the opposite direction of N and U, which are going in the same direction, and V's magnitude is 5. So how do I use what I've done so far to figure out what V would look like? Maya?
You can just do -1/5 times vector n.
Times what?
The vector n vector.
Times N? That's only going to give me a vector, that won't end up with a vector that's magnitude is 5 though. That'll give me a vector that's 1/5 as long as this, but this vector isn't 25 units long, so that vector wouldn't be 5 units long, right? Now, I see what you're doing. The negative is right? We need the negative in there to get it to point the other way. But how do I get a vector that I'm going to end up with a vector whose length is actually 5?
-5 times u.
Okay, right. U, the advantage of doing U first is U's magnitude is 1. So if we do any scalar times U, the new vector will be, the magnitude will be equal to whatever the scalar is, right? Because we're starting with a magnitude of 1 if we start with U. It's more annoying if we start with N, because that vector is 17 point something units long, right? So we could say V is -5 of U. The 5 times U will make its vector, make its magnitude 5, and the negative makes it point the other way, right? So I could just take these guys and multiply them all by -5, right? And in terms of writing the vectors down, I was showing you different ways of representing the vectors. This is what IB commonly uses with the columns. You can also write vectors like this, right, with components. Or what's the third way? The IJK, okay? I'll use that here since I'm a little squished on vertical space here. I'll write this answer using that with I's, J's, and K's. So I would have, it would be 35 over root 299 I, and then -5 times the middle, so minus 45 over root 299 J, and then plus 65 over root 299 K. Yeah.
If we get full points, we just left the scalar in front of the vector, or do we have to?
So it depends on how it's asked. Like on the warm-up, I just said find the components. If I had on the test something that was asking you like fill in the blanks, X component, Y component, Z component, these are the numbers you want, right? And I might ask that to make sure you don't use these numbers, that you incorporate the scalar. But if I just say find the vector, that and that are the same, okay? Does that make sense? And this also clearly identifies the components because the components are just the coefficients of I, J, and K, okay? Everyone's also okay with the fact that if you write it with I's, J's, and K's, you're like adding and subtracting the I, J, and K vectors. It's not commas like that, right? If you write these as commas, it's 3 separate vectors. It's not one vector with those 3 things. Does that make sense? Okay. Any other questions related to any of this stuff? This is the stuff that ties into things we did yesterday. So if you're okay with all of these things, you're pretty good with the basic stuff from yesterday. Is that fine? Okay. So the new stuff today is for most of the vector unit actually for IB. Like there's lots of stuff you can learn with vectors, but what IB mostly tests you on with vectors is your ability to analyze like geometry style problems, like stuff with lines and planes in 2 and especially 3 dimensions. Like I said yesterday, we won't really go into anything beyond 3 dimensions, but there's a lot of 3-dimensional stuff in the vector unit for HL. Like they'll talk about in space, here's this plane, here's this line. Where does that line intersect this plane? Or are these 2 lines parallel or not? Are they perpendicular or not? Stuff like that, okay? So the kinds of questions you're used to, but where you've probably had more experience doing this in 2D, and even though some 2D stuff does still come up, it's more common that things will come up in 3D because that's where vectors like become necessary. We don't have to use vectors in 2D, we can, but they become more essential in 3 dimensions, okay? So the first place where that does come up is when we're writing the equation of a line. Okay. All right, so I made this picture in GeoGebra because my 3D drawing skills on the board are not great. But there's a lot going on in this picture, and I want to kind of explain what this is, but I think it's most helpful to explain this if I can make a comparison between what you're used to in 2D and what we do in that case, and how this is going to accomplish the same thing in 3D, okay? So let's start with just the simple 2D. If I had the regular Cartesian plane here and some line in it, and I wanted you to write the equation of that line in 2D, what information do I have to give you about that line that would uniquely define it so that you could write its equation? Like, what's the least information I can give you that's enough to describe that line and distinguish it from all the other lines? 2 points is the simplest, right? So if I gave you any 2 points, there's only one line you can draw through those 2 points. What if I didn't want to give you 2 points, though? What if I only gave you 1 point? Let's say P0. Now what else do I need? Like, that's not enough, right? Because there's an infinite number of lines that would pass through that point. So if I don't give you a second point, what else can I give you that would still uniquely describe that line? Direction. And how do we usually describe direction in 2D? Slope, okay? So if I told you what the slope was, slope is change in y over change in x, right? That describes the path that that line should take through the point. And once you have the path and the specific point that you need to pass through, there's only one line that will do that. Okay, does that make sense? This is problematic though in 3 dimensions. Okay, we're going to do the same kind of thing. So this diagram, the goal is to write the equation for this black line that has A and B on it, line AB. Okay, now suppose I only gave you point B. Okay, so you know the coordinates of B, but you don't know anything else. Do you see that slope here in 3D doesn't make sense as enough to like describe what path the point is, or the line is taking through that point? Because slope is only the change in y with respect to x, so how does y change with respect to x? But now there are 3 variables, x, y, and z, and any 2 of them could have like a slope-like value, right? How does z change with respect to x? How does z change with respect to y? How does y change with respect to x? So if I just give you one of those, like how does y change with respect to x, that's not enough to describe exactly what path am I taking through this point, okay? So what plays the role of slope over here is what's called a direction vector, okay? The gold vector here is describing the direction that the line would go in. Now, vectors only have one direction. Lines go forever in 2 directions. But if you specify the direction vector, then you know the line goes in that direction and its opposite. So giving one vector is enough to describe what path the line should take, okay? Now, where that vector is located and how long it is are not important, right? So I just fixed this direction vector onto the z-axis. So the rest of what's going on here, the red, green, and blue lines are just the coordinate axes, right? You have x and y, the red and green, and then z coming straight up here. So D is a point on the z-axis that's not related to the line. It's just I started the direction vector at that point. But we would not care. It's not important where that vector is located or even how long it is. We're only going to use it for determining the path that the line we're interested in takes. Does that make sense? Okay. Now, the other thing I have is this purple vector here, starting at the origin, landing on point P, or point B. Do you remember yesterday we talked about what do you call a vector that starts at the origin? What's the name we give to that? Any vector that starts at the origin, it's called a something vector? Position vector, okay? So this is a position vector, starting at the origin and ending at the point that you know is on the line. If I give you that vector and the direction vector, that's the 3D version of giving you a point and the slope in 2D, okay? I'm telling you where the line is located, at least one point of it, and I'm telling you what path the line should take. So we want to be able to say, since we know in 2D, giving you a point and the slope is enough to determine the line, then doing the equivalent of that in 3D, telling you one vector that points to a specific point on the line and another vector that describes what direction the line is going, that should be enough to describe this whole line. But the way we describe the line is to have a generic position vector. This black vector here starts at the origin also, and it's pointing to P. P is just representing any point on the line. So B is a point you know. P could represent any point. It's not meant to represent a specific point. So we're trying to write a general form for what that position vector should look like. How do I make a position vector that will start at the origin and land anywhere on this line? Okay? And you see I have a little triangle of vectors here, like I did yesterday. So I've got the position vector going to the point I know. Then I've got a vector that travels along the line. And then I've got another position vector from the origin to some other point on the line that could be any point. Okay? When you see three vectors arranged like this, one starting where another left off, and the third one going from the beginning of the first to the end of the second, do you remember that's the visual representation of doing what with vectors? We saw that yesterday, where I've got like this triangle forming of vectors. What's actually happening with those vectors? Yeah, you're adding, right? In this case, I'd be adding the original position vector, the purple one, to this vector along the line, and the black vector is the sum of those two, okay? So what we're saying is, if you want to make sure you land on any point on the line, what you do is first get to the line. That's the vector we'll give you, right? The original position vector. And then to get to any other point on the line, once you're already on the line, you just need to add a multiple of the direction vector. As long as I go in this direction, or its opposite actually, and I started on the line, I will end up somewhere else on the line, right? Now, what point you land on depends on how long the multiple of the direction vector is, right? If I pick this actual direction vector up and put it on so that it started at B, does it look like that length vector starting at B is going to take me right about to where A is, right? So if I take the original position vector and I add D itself, the direction vector starting from D, if I add that itself, that'll take me to point A. If I wanted to get to the point I showed here as P, I need some fraction of that direction vector, right? Maybe that looks like a fourth of it or something like that. So the original position vector plus a fourth of the direction vector takes me here, okay? If I took half of the direction vector, I'd end up about right here, right? One direction vector would end here. If I want to go way down here, I just need a bigger multiple, right? So like if I take two of these, I'm way down here, three of them, I'm down here. But you see, like for every possible scalar multiple of this, I get to another point on the line, okay? What about if I wanted to get on the other side of B? Like these points are on the line too. If the direction vector is going this way, but I want to end up here, what kind of scalar should I use in front of the direction vector? A negative scalar, right? All the negative scalar values correspond to points up here. What if I want to just stay right here at B? What's the scalar? 0, okay? So does it make sense if you have an infinite number of choices for what scalar multiple you want to add on to here? For every different choice of that, you get a different point on the line, okay? So the generic position vector to any point on the line is just the sum of the one position vector you know, and then multiples of the direction vector. Infinitely many different multiples of the direction vector. So that leads to this. This is what is called the vector form of the equation of a line in 3D, okay? It starts out with a generic position vector, x, y, z. It's equal to a specific position vector. So that first thing has to be a position vector that goes to a point you know is on the line. So those components, x0, y0, and z0, because it's a position vector, the endpoint coordinates and the components are the same. So those components are just the coordinates of one point you know is on the line. And then to that, you add multiples of the direction vector. But we don't want to add a specific multiple here. We want a parameter there, something that can change, so that for every different value of the parameter, we get to a different point on the line. And since there are infinitely many choices for t, every different choice of t corresponds to a different point on the line. If you consider all the possible values of t, that's giving you all the possible points on the line. Does that make sense? All right. So that's vector form of the equation of a line. Now, if you are in or have taken multivariable already, and you've done this more recently than back in pre-cal, you probably remember that there are multiple forms of equations of lines in 3 dimensions. The vector form is the first form, but you need to know 2 other forms, and you need to know how to convert between the 3 forms, because depending on the information that you're given or what you're going to do with the line in terms of solving problems, sometimes you need the line to be in one form versus another because it's more convenient to work with the process that way. So we will have not only vector form, which is here, right? But there are two other forms, the next of which is parametric. Now, parametric form you guys have actually seen in this class already. Do you remember in the matrix unit when we were doing the finding solutions to systems of equations, and you had the infinite solutions case, like you do row operations, you get row echelon form, and you get infinite solutions? How did the matrix look to tell you there's infinite solutions to the system? What's the bottom row? All zeros, right? Okay, and when you got all zeros, that means the planes, each equation you had represented one plane, the planes are intersecting in an infinite number of points, which almost all the time means they're intersecting in a line, okay? And in that situation, we had the process where you had the free variable, you would let z equal t, and then you back substitute and you solve for x and y in terms of t. We were getting parametric equations for the line, okay? But if you already understand this form, going from this form to parametric form is just, instead of writing a single equation with vectors in it, you write separate equations for each one of the components, right? So you have an equation that just deals with x, another one that just deals with y, a third one that just deals with z. And you make the equations by just looking at the vector equation and considering only one component at a time. So if I take this and only pay attention to the x parts of the vectors, you would have x itself on this side equals what? X0 plus AT, right? And the middle equation for y would be y equals y0 plus bt. And then at the end, you'd have z equals z0 plus ct. So those are the parametric equations, okay? When we did this in the matrix unit, the z equation, because we were using the matrix ideas and the free variable, z turned out to be t every time, right? That's like having z0 be 0 and c be 1, right? And then based on that, we got expressions here. One thing to keep in mind that's different with how equations of lines in 3D works compared to equations of lines in 2D, I guess there's some parallels. If we have slope-intercept form, this is unique for a line, right? Like this line, I don't know, maybe it's hitting the y-axis at 3, and maybe that slope is 1. So maybe this equation is y equals x plus 3. And if I'm in slope-intercept form, that's the only way to represent that, okay? But if I'm in point-slope form, I could represent this same line in infinitely many different ways, right? Because if I have y minus y1 equals the slope times x minus x1, I can choose what I want for this as long as I'm picking a point that's on the line. So infinitely many ways to represent it, right? In 3D, it works the same way. This is not a unique representation of a given line. Like this just has to represent the coordinates of one point that's on the line, but it could be any point that's on the line, right? And the direction vector here, that particular vector is a valid direction vector, but once you have a direction vector that's valid, any vector parallel to that, meaning any vector that is a scalar multiple, would also work, right? So these are not unique. If I can make different choices for these and these, I could have different equations down here too. Okay, so it's not like there's one set of parametric equations that represents this line. If you change anything, you definitely are talking about a different line.
If you're like coefficient vector, I guess next to the t.
Yeah.
If it's any scalar multiple, then would it like evolve differently over t? Like spatially, yeah, they're the same, but like.
Right. So what would change is like what t value would correspond to what point, right? If you change these or these actually, right? Then which t generates which point is different. But if you considered all the t's, you would get the same set of points on the line either way. Okay, does that make sense? All right, now this might be more at the forefront of people's minds if you're doing MVC now or did it more recently than when you guys were all in pre-cal. Do you know what the third form, we have vector form, we have parametric form. Do you know what the third one's gonna be? Symmetric, okay, is that the term you use in MVC? Yeah. Okay, so IB calls it symmetric or Cartesian form, and I always forget which one you guys use in MVC, but you should know that those two terms are interchangeable. So if you see, like sometimes they're going to ask you for the equation of a line in a specific form. They'll say write the vector form or write in parametric form or write in symmetric form the equation of a line, and then you have to write it in that particular form. If you see symmetric or Cartesian, those are two different names for the same thing, okay? Do you know how to get that? It's easiest to get from the parametric equations. How do you go from this form to that form? Bihan?
Isolate t.
Yeah, all of these have a t in it. So you solve for what t is equal to in each of these cases. So t will be equal to some x stuff in this equation, some y stuff in this one, and some z stuff in this one. And if those x, y, and z expressions are all equal to t, then they're each equal to each other, right? So if we have it like this, if I isolate the t in each expression, x minus x0 over a is equal to t from this one. So that form of t is equal to this, which is what t is equal to in terms of y, which is equal to that last expression, z minus z0 over c. That's what t is equal to in terms of z. Okay? That equation looks the weirdest because it has two equal signs in it, right? That's kind of bizarre. And you're going to notice as we start solving problems related to this stuff that different forms are more useful depending on what you're trying to do, okay? This form, I will tell you, shows up the most as the way a line is given to you. Like in a problem, they might say, here's a line, and they give it to you in symmetric form, and then they ask you questions about it, okay? This is sort of like the most condensed way to write it, even though it does have the double equal sign. But you don't have to use vectors, and you're writing one string of equivalent expressions instead of three separate equations. Okay? Thank you.
Isn't there formula sheets?
That is a good question. There's a lot of stuff in the vector section. I don't remember offhand. You have to check your packets to see if it's in there or not. I don't know if they just lay out what those forms are or not. I can look in a little bit too. Okay? Let me point out one other thing that I remember always comes up with the symmetric form. This form is also good in that you can read off some information easily about the line if you see it in symmetric form. Like, do you notice the denominators in the symmetric form? What are they giving you? What are those a, b, and c values? That's the components of the which vector?
The direction.
The direction vector, right. So like if you want to know if two lines are parallel, if you have equations there in symmetric form and you want to know if two lines are parallel, lines would be parallel if their direction vectors are parallel, right? So you would want to see either the same direction vector, or if they're not the same, one should be a scalar multiple of another, right? You have to be a little careful though. Sometimes they'll give you something that looks kind of like symmetric form, but isn't technically quite in the right form, like something like this. Oops, Z. Let's do that. All right, you see how this is basically in symmetric form? But if I asked you to identify a direction vector for this line and you just said 4, 2, 5, that's not actually a vector that's pointing in the direction that this line is going. Do you see what the problem is here? Like, why can't I just read this off as 4, 2, 5? The coefficient of z is an issue. That's one issue. There's actually two issues here. And y is negative. These are only going to be the direction vector components if the coefficients of x, y, and z are all what? What are they all here? 1. If they're all 1, then you can read the denominators as the direction vector components. So the x part is fine. But here, I would want to flip this around. So I would write y minus 5 on the top. But if I want to make this equivalent and I switch this to y minus 5, then this needs to be negative 2. And then here, I want z to have a coefficient of 1. So I could factor out the 2, right? But then I don't want the 2 next to the z. I want to bring it down here. So if I have 2 on the top, that's the same on the bottom as having 1/2. So this would be 5 over 2, right? So this is z plus 5 over 5/2. And then you could read a direction vector. Like one direction vector would be 4, negative 2, 5/2. And remember, once you have a direction vector, any scalar multiple of this also works. So another one would be 8, negative 4, 5, if you don't want the fractions. But notice that is not the same as 4, 2, 5. Like that is not a scalar multiple of this. So if this is a valid direction vector for the line, and this is not a scalar multiple of it, then this is not. And the reason it's not is you don't have the coefficients as 1s for x, y, and z. Does that make sense? Okay. All right. Okay, a couple examples here. All right. this one, I gave you, this is what Jinwoo said actually at the beginning, right? The minimum information to uniquely determine a line, if I don't want to give you anything else, is 2 points, right? There's only going to be one line you can possibly draw through 2 points in space. Now, let's give these points some names. Let's call this point A and this point B, okay? If I want to write the equations of the line through this point in all 3 forms, let's do it in the order I just gave you. So we'll start with vector form. What do I need for vector form of the equation of this line? Like, what's the 3D version of giving you point and slope?
The vector,
The what vector?
the direction.
Direction vector is one thing, okay? So I'll call that D, okay? Do you know how to get that? These are only points, right?
Do the each like x2 minus x1.
Yeah, okay, so one direction vector, I actually have some choices here, right? I could do the vector from A to B if I want. Could I also do B to A? That would be fine, right? Actually, any scalar multiple of this, right? We don't care how big this vector is, we just need a direction that the line travels in. So if I want to do AB, which way do I deal with the coordinates if I want the vector that starts at A and ends at B? Which coordinates do you start using? B's, and you subtract A's, right? So the X component would be -3, and then the Y, and the Z, -3 again, okay? Now, if you don't like those negatives all there, 3, 2, 3 is also valid, right? Any scalar multiple of your direction vector is valid as a direction vector. So I can use that, I can use the negatives. If this had been 3, 6, 3, and I can take the 3's out and use 1, 2, 1 instead of 3, 6, 3, right? That would be fine too. Okay, I need something else besides the direction vector. What else do you need to write the vector equation of the line? Direction vector is one thing you need, but you need a second thing. Position vector. How do you make a position vector? They start at the origin. This is how IB would tend to write it. OA is the position vector that starts at the origin and ends at A. So that vector would be 1, 2, 6, right? Because its components are going to be the same as the point you end at, since you're starting at the origin. Okay? All right, now I have all the stuff I need. How do I actually write the equation? What do I write first? Ma'am?
It would be OA plus T times AB.
So like 1, 2, 6
Yeah.
plus T times that,
Yeah.
and that's it?
Equals, I guess, RT.
Equals, yeah, you need something on the other side, right? So you can have, what I showed you before is you need like a generic position vector like that. You could also do something like R, okay? In multivariable, you probably do like R of T sometimes, right? So you can just do R instead of that, okay? But I will say this is a point that IB harps on, okay? A lot of people, when they're asked to write vector form of the equation of a line, lock into, okay, I need a position vector and I need a direction vector, and it's position vector plus T times direction vector, and they only write that, okay? But if it says write the vector form of the equation of a line, what is the symbol that must appear in something that you're asked to write if it's called an equation? You have to have an equal sign. And if you write down an equal sign, you need things on both sides of the equal sign, right? You can't just have like blank space equals other stuff, right? So usually when IB asks this, like if they just wanted the vector form of the equation of the line, this would be 2 or 3 marks, and one of the marks is just for remembering this, okay? Because they have seen so many people forget this that they've decided we're gonna make that worth a point just by itself, okay? So you get a point just for that, and then 1 or 2 other points for like filling in the rest of the stuff correctly. Okay, it said all 3 forms. So parametric, we just write separate equations for x, y, and z. But once you have this, you just read off the equations the other way, right? So x is going to be what?
Are they not dot?
1 minus 3t. Y will be 2 minus 2t. And finally z, 6 minus 3t. Okay? That's parametric form. We did vector form. Last one is symmetric form. Symmetric form, we just want to isolate the t's and write down what the x, y, and z expressions are that are equal to t. What is t equal to in terms of x? minus 1 over negative 3. That is equal to what in terms of y?
Y minus 2 over negative 2.
Over negative 2, okay? And that is equal to z,
Minus 2 over negative.
good. Okay, there we go. All done there. Make sense? Miha.
Could you also write it like the negative version of that? Like scalar multiplied by negative 1.
Which, in this one?
Yeah.
Like 1 minus x and that kind of stuff?
Yeah, but if you kept the negative 3 in the denominator, and it would just be going backwards, right? Because it goes in both directions.
Mm-hmm. Right.
And if you were inconsistent on your 3 forms, but all 3 were like correct.
I don't think a question, like this is for practice,
Okay.
I don't think they would have you do all of this.
Okay, well-
What's more likely is they would ask you for one of these forms, and then they might ask you to do something with it where maybe you need to change it to another form. But I don't think that this is like belaboring the point. Like, can you write the equation line in as many ways as you know how to do it? So I don't think that's going to be an issue. Yeah, as long as you're, it doesn't, you could do some sort of transformation on this, and as long as it's still correctly representing the line, you would get credit. Yeah. Okay, I've got one more. I guess it's 2 questions related to this line. So new line, xyz equals, oh, actually not new line, right? That is the line. xyz equals 126 plus, oh, new parameter name, what is that? Lambda. Okay, you're gonna notice we're gonna do a bunch of stuff with equation of lines, and we're gonna use multiple different parameter names because, especially if you're talking about multiple lines in the same problem, you want a different parameter name for each one. So you don't want to use t in one line and then have to talk about another line and use t again. So lambda's common, t's common, mu, which is the letter in the Greek alphabet that follows lambda, is also common. S is also common, but I hate using s because when I write s's, they look like 5s, and I keep getting stuff wrong because I forgot it was a s, not a 5. So I try not to use 5s. But you can, there's plenty of letters available, right? You don't want to use anything you've already used, like don't use X, Y, or Z as a parameter name, obviously. There's some bad choices like L's and O's look like 1s and 0s, right? But really, if you want to use like sunshine, right? Or, you know, whatever, emoji guy, right? That's fine. I don't recommend spending a long time drawing your parameter names, right? But it doesn't really matter what we call that, okay? But it does matter to use a different name for a different line if you're talking about multiple lines in the same problem, okay? Vector form of the equation of line through this point that's parallel to line L. So vector form starts with x, y, z, right? Equals, now what do I want to put here in the position vector spot? I want this, right? I want to make sure the line goes through this point. The way I can do that is make that the position vector, right? And then if I want it to be parallel to L, how do I make sure it is? Same direction vector. Technically, oh, I need a little space there, right? I need a parameter name. So I'll use t since they use lambda. I technically don't need to use the same direction vector as long as it's a scalar multiple, that would be good enough, right? And then the last one here, perpendicular to the YZ plane. The YZ plane in this picture is the plane of the screen, right? Do we have a vector that makes a right angle with the board? Yeah, the x-axis, anything along the x-axis. So like I, 1, 0, 0 would work there, right? Now this is asking for a parametric equation, so I would have x, y, and z separately. I would still have my 7, 1, and negative 3, but then I would have 1, 0, 0 here. So I'm going to write this, even though for these last two you wouldn't need them, right? It's 1t, 0t, and 0t. So x is 7 plus t, y is just 1, and z is just negative 3, right? So in that line, only the x coordinate is going to change. The y and z coordinates will stay 1 and negative 3 the whole time. Okay? All right. Homework 2 tonight, and then I will check homework